Hello everyone. So what's the reason for the diminishing number of students? It can't be the material being tough. We're taking it easy so far. Maybe the notes should be online? Or we should cut off the screencast? Alright, I'll keep those just to be nice, but there's nothing like real class, right? It's like coming to a concert instead of streaming the same music. Okay, so today we'll start talking about Fourier series. You may have heard this name before. Fourier, Joseph Fourier is a French dude who lived 2 centuries ago. And he gave us all this stuff that we have to worry about now. Alright, so Fourier series is about taking periodic signals and decomposing them into single frequency sinusoidal components. Okay? If this means nothing to you now, don't worry, in 15-20 minutes it will probably mean something. Right? So before we jump into the Fourier series itself, we will first do a little refresher on periodic signals. And today we're in continuous time. Okay, nothing discrete. So when I talk about a signal x, that's a function of a real valued time variable t. Okay? So what is a periodic signal? X is periodic if there exists, this sign means there exists. It's convenient to write, shorthands when you're writing a lot of things. If there exists a period t such that no matter what little t I select, the moment I add capital T to it, I'll recover what I had before. Okay? So for all t. Okay, so if you haven't seen these before, this means for all. This means there exists. Okay, I'll try not to use them, but I may when I'm getting tired of writing stuff down. Okay? So that's the definition of periodicity. Is it all clear? Self-explanatory, right? All right. So the smallest such t is called the fundamental period. The reason we need to distinguish the smallest such t is because, if you wake up every 24 hours, that's your period, right? You also wake up every 48 hours. You also wake up every 72 hours. So integer multiples of t are also periods, right? So then it's convenient to deal with the smallest possible. And we call that the fundamental period. All right, so here's a simple example. So we have a sine of 2 sinusoidals. The first one is cosine 2 pi by 3t. The second term is sine pi over 10t, right? So what is the period of the first part? Forget about the sine. What is the period? What is the fundamental period? It's 3. For the other guy, it is 20, right? And of course, integer multiples of those are also periods, but these are the fundamental periods. So what is the period of the sum? The period is 60, which is the lowest, lowest common multiple of 3 and 20. That's the smallest common period. Okay? 60 is of course also a period for cosine 2 pi by 3t. It's also a period for sine pi over 10t, and that's the smallest one possible where the two agree. So then a question arises from this example: is the sum of two periodic signals itself periodic? Aha, I got you. How many people think no? you don't count. Okay. All right. So if I ask a question, usually there's a trick. Why else would I ask that? Only to make you say the opposite and embarrass you. Right? So the answer is not necessarily. I mean, it's not yes or no. Sometimes it's yes, as you saw in an example. But you remember in the example, we had to find the lowest common multiple of the two periods. Does such a lowest common multiple always exist? What is the lowest common multiple of, say, 2 pi, 2 pi and 1? Can you find, actually these are, wait. Can I find, so let me put it this way. So what we are looking for here is, n, do there exist, are there integers? Yeah, when I say lowest common multiple, by the way, I mean integer, okay? So integer multiples. I don't know what I'm saying. So, okay, let me tell you what I'm trying to say, and then you use the accurate words. Are there integers m and n such that m times t1, that's the period of the first guy, right, is equal to n times the period of the second guy, right? Are they integers? Well, in this example, yes, but what if, that if there are, that means T1 and T2, the ratio of T1 to T2 can be written as n by m, which is rational. No. In general, no. Well, if the ratio is not rational, so let me give you an example. Take cosine 2 pi t plus, say, sine t, right? The period for this guy is 1. The period for this guy is 2 pi, right? Their ratio is not rational, so I can never find an m and n where they actually meet. Okay, does that make sense? So the answer to the question is yes, if the ratio of the periods is a rational number. Okay? But in general, it's no, because they don't have to be rational. Does that make sense? Okay, so we have to be a little careful when we talk about the sum of two periodic signals. They may or may not be periodic themselves. Okay? All right, so let's continue. So, yes. Fundamental period you can say 0 because 0 is the smallest thing you can. Well, in that case, yeah, we have to make an exception for one of those being both of them being non-zero for that test to make sense. You're right. Okay, so last time I tried to convince you, I don't know successfully or not, that it's better to deal with complex exponentials, even though they look scary at first, e to the j omega t types of signals, instead of all these sines and cosines. How many of you are convinced? How many need more convincing instead of? Well, I mean, I think over time it will sink in. So our preference is to deal with complex exponentials because the algebra that's required in these Fourier series and also in the Fourier transforms that we will see later becomes a lot easier. It becomes very efficient when we deal with e to the j omega t types of terms, right? So in particular, when you do this, you don't have to, e to the j omega t with an appropriate coefficient will represent either a cosine or a sine or any other shifted, another cosine type of thing with a phase shift. Okay? If I, for example, want to express cosine omega t plus some phase, of course, if I choose the phase appropriate, it becomes a sine, right? So I can write this as, do you remember the expression for cosine in terms of complex exponentials? E to the j something plus e to the negative j that something, right, will give us 2 times the cosine. So if I divide this by 2, I'm going to recover cosine. That something is the argument here. So it's omega t plus phi here, and omega t plus phi, right? So these follow from the things we discussed last time, right? So this is going to be 1/2. Now I can also, that's another nice thing about exponentials, e to the something plus something separates as e to the something times e to the other thing, right? So I can write the first term as e to the j omega t, e to the j phi, and the other term as e to the j negative j omega t, e to the negative j phi. So that way we represent it in this form, 1/2 e to the j phi, which is a complex number that depends on whatever phi is, right? Times e to the j omega t plus 1/2 e to the negative j phi, which is another complex number, times e to the negative j omega t. Okay? So with that representation, we cover everything between sine and cosine, any kind of phase difference. All they change are the coefficients of these terms, right? Okay? So the phase of the sinusoidal oscillation affects the coefficient and nothing else. The e to the j omega t term remains intact. So I don't have to deal with sine, cosine, phase, and all that stuff, right? They are all swept under the coefficients. Another benefit of this is that, if I look at, let's say, cosine, some number a, cosine omega t, plus another number b times sine omega t. Is that periodic? Yeah, they are of the same frequency, so they have the same period, right? So the sum is periodic, but there's only one frequency involved, but I can't write it as either a sine or a cosine, right? But nevertheless, I can bring it to a similar form with a coefficient times e to the j omega t plus another coefficient times e to the negative j omega t. How do I do that? Well, again, it's the same trick. So I write this as 1/2 e to the j omega t plus 1/2 e to the negative j omega t, and I write this as 1/2j e to the j omega t negative 1/2j e to the negative j omega t. So if I put everything together, I have 1/2 from here and 1/2j, a over 2 from here, and 1/2j times b from here. 1/j is negative j, right? So I can just write this as a minus bj by 2 e to the j omega t plus a plus bj. Is that correct or not correct? Yeah, because this term here, 1/j is negative, so the negatives cancel out, times e to the negative j omega t. So it really looks like the previous example, right? So except that the coefficients are a little different now. Okay? So all kinds of sinusoidals of the same frequency, no matter what their phases are, or even if I'm summing them up, I can put them in a very uniform format. Something times e to the j omega t, something else times e to the negative j omega t. Okay? And in these two examples, so this was the first example, and this is the second example, Now, if we examine the coefficients of e to the j omega t and e to the j omega t in each case, do you see a pattern? Compare the coefficient of e to the j omega t in each example to the other one. Yes. They are complex conjugates, right? Here, if I take this term, if I take this, the complex conjugate of that, j phi star, is just 1/2 e to the negative j phi, which is the same as this, right? Similarly, the complex conjugate of this is that, right? So that was no coincidence. This is a general property of any real valued expression. So what do I mean by that? If I take a function, a signal that looks like this, some number c times e to the j omega t plus another number, a complex number, times e to the negative j omega t. So if this x of t is real valued, then the coefficients of e to the j omega t and e to the negative j omega t must be complex conjugate. In other words, c must be the same as d star, or c star is the same as d. Same thing, right? Why is this true? Does anybody want to argue why? Yes. In what? Oh, if you expanded them out. Yeah, that's one way to do it. So one and slightly painful way of doing it is to split C into its real part, imaginary part, split D into its real imaginary part, expand them out, all kinds of cosines, and package them together. Unless C is equal to D star, you will see that an imaginary term remains. Okay? There's a simpler argument, a lot more elegant. Real means x star of t is equal to x of t for all t, right? If x is real valued, this has to be true, right? So let's write x star. If x is this, right, what is x star? Well, the star of the first term, if you have a multiplication of two terms, if you star the product, each term gets starred, right? So then you get c star times e to the j omega t star. But starring e to the j anything is the same as flipping the sign, so it becomes e to the negative j omega t. Okay, so we have taken the conjugate of that. Now let's take the conjugate of the second term. That will give me d star times e to the negative j omega t. So if x is real valued for all times, for all t, then the coefficients must match. So c, which is the coefficient of e to the j omega t, must match these positive, must match d star, and d, which is the coefficient of e to the negative j omega t, must match c star. Well, that's basically saying that c must be equal to d star. Okay? So the reason I'm going through this is to make some sense of the concept of a negative frequency, right? Because when I took these sines and cosines and written them in terms of e to the j omega t, all of a sudden I have this e to the negative j omega t term popping up, right? Negative omega, what does that mean? Negative frequency? What's the meaning of that? The answer is here. The answer is that it doesn't mean anything. It's just a phantom, okay, that's there to balance out the imaginary compounds so they cancel, so you can recover the real term. Okay? So it's just a convenience. I mean, it's a necessity of dealing with e to the j omega t, which has real and imaginary parts, and imaginary parts have to disappear somehow. And you make them disappear by adding these negative frequencies. Okay, so negative frequency is just a convenience. It's a little price to pay to take advantage of these e to the j omega t expressions to unify all sinusoidal expressions. Do you have any questions? So are you going to freak out from now on if you see negative frequencies? Now you know what they mean. Okay? All right. So with that prelude, we can go into Fourier series. So if you have any questions, this is the time to ask. No. I mean, no, I don't. I mean, the convention will be number times e to the j omega t. Okay? And naturally, if it's a sine or cosine, 1/2 will go into the coefficient. That's all. Well, of course, yeah. I mean, I did. This is the coefficient here. But I'm not going to write it as 1/2 times coefficient times e to the j omega t. 1/2 will be encompassed by the coefficient. Yes. Okay. So, who is Fourier anyway? Let me go to class note where I included a picture of the guy. This is the guy. That's him. Nice drawing. I'm sure nobody will have a drawing of him like this, but you can read about him. He's a French mathematician who lived long time ago. And so the main idea in Fourier, okay, this is too slow. Let's go back. The main idea in, and by the way, you know, the French have the habit of, they keep writing after they put all the sounds on the paper. So the last R in this case, you don't really pronounce it. I think it's a Fourier, right? So the main idea in Fourier series is that if I give you any periodic signal, you can decompose it as a sum of sinusoidal components with increasing frequencies. Okay? More precisely, so given X periodic with period, fundamental period T, period T, in which case, I'll stand back for a second. When I give you a period T, what is the frequency of this? What is the fundamental frequency? If you have a sinusoidal, single frequency with period T, the frequency is, okay, so I'm going to call this omega sub naught, not to distinguish the fundamentalness of the frequency, okay? Fundamental frequency. That is 2 pi by T. Okay, but once that's multiplied by capital T, you're back to 2 pi, so you're back where you started, right? So that has the unit of radians per, if you're using seconds per time, radians per second. Okay? There is another way to represent frequencies where you don't put the 2 pi, you just say F is equal to 1 over T. Okay? In that case, the unit is 1 over seconds, and that particular unit has a name. It's known as Hertz, Hz for short. Okay? So if I give you a frequency in Hertz, you can multiply it by 2 pi and convert it to the comfy and familiar omega form. Yes? What's that again? Well, I mean, it's just the convenience of putting it in terms of pi. I mean, so if I tell you I have a sinusoidal signal, with frequency 50 hertz, right? What is that sinusoidal signal? Sine 2 pi times 50t, right? So that when t becomes 1 over 50, you get pi, right? So we find it more convenient to combine these into an omega instead of keeping this f. Okay? All right. Okay, that was a detour, so I haven't started talking about periodic signal. So, Fourier series. So let me move this down. Now I'm going to really talk about Fourier series, okay? So given this periodic signal with period t and therefore fundamental frequency 2 pi by t, the idea in Fourier series is to expand x, the periodic signal, as a weighted sum of e to the j omega 0 t, right? That's a sinusoidal basically that has only one frequency component in it, and that's the fundamental frequency of our periodic signal, as well as e to the j 2 omega 0 t. Now the frequency is doubled, right? And e to the j 3 omega 0 t, and so on, okay? And of course, once I use these, I also need to use their phantoms, right? So their shadows, whatever you want to call them, you need to also introduce these guys, right? E to the negative j 2 omega 0 t, e to the negative j 3 omega 0 t. Why do I need all these multiples of the fundamental frequency? Just imagine I'm dealing with a periodic signal that looks like this. It's like a square wave, only it's periodic, okay? So, let's say t is 1. T is 2 in this case, so 1/2, okay? Negative 1/2, right? So the period is 1, right? So could I possibly represent this with a single sine function or cosine function with frequency equal to omega 0? So t is 1 in this case, right? And omega 0 is 2 pi by t, which is 2 pi, right? If I use a cosine 2 pi t, can I possibly reconstruct a square wave like this? Sine is too smooth. This guy is too edgy, right? So it's not going to work. So the idea is to use not just sine 2 pi t, but also use sine 4 pi t, which is a much faster oscillation. Also sine, cosine 6 pi t, 8 pi t, 10 pi t, all the multiples, and multiply them with appropriate coefficients so that their sum converges to something that looks like the square wave. Does that make sense? So that's why I need higher multiples of the fundamental frequency, right? And that alone will not be enough, because what if, the signal has a bias term? What if this is 1 and this is 2, right? Then the average of the signal is not 0, right? So those numbers, when you average them over one period, they're all going to give you 0, right? They're not going to give you a non-zero average. So to accommodate a bias term, you also have to use a 1, a constant term. So you can raise these things up or down, okay? So the point is that we can take any periodic signal and decompose it into a weighted sum of these basis functions. A constant term, a sinusoidal term with the fundamental frequency, a sinusoidal term with twice the fundamental frequency, a sinusoidal term with 3 times the fundamental frequency. In principle, you may have to go to infinity in multiplying the fundamental frequency. Okay? So, I'm going to write everything more compactly. So, the idea is to decompose x in this form. Sum over k. K is the index that tells me which multiple of the fundamental frequency I'm talking about. Okay, so that will go from negative infinity to infinity. AK, that's the coefficient that I have to multiply each of these basis terms with. So A0 for the constant term, A1 for these guys, and so on. Okay, AK times e to the j k times omega 0 t. So when k equal to 0, this is equal to 1. Okay, so this is again equal to e to the j omega 0 t when k is equal to 1. So that is the fundamental frequency. K equal to 2 gives me e to the j 2 omega 0 t, and that is twice the fundamental frequency. Okay, so these terms have special names. People usually call the bias term, the constant term, k equal to 0, the DC component. Why DC? Because DC is direct current, and direct current, constant value, things like that. I think circuits guys, got excited and called it DC, and it stuck. K equal to 1 is the fundamental frequency. And k equal to 2, people call it the second harmonic, meaning that it's basically, twice the fundamental frequency. And for that reason, you can call the fundamental frequency the first harmonic. So going back to our square wave example, a sine function with frequency 2 pi would give us something like, that repeats. How do I do this? Yeah, so it would give me something like this, right? So that would be the first harmonic. The component with the same, the fundamental frequency 2 pi would be the first harmonic. The one that oscillates twice as fast, I'm not going to do this right, will give you the second harmonic. And then you'll get the 3 harmonic, which changes more rapidly. And the idea is that if you multiply these things with appropriate coefficients and add them up, you will recover in the limit something that looks like the original periodic function. All right? So that's the claim, and we'll investigate this today in what remains of this lecture. Do you have any questions so far? No? Okay. That can mean two things. Either it's very clear or completely unclear. So I'm going to start with a very simple example. And I'm going to call it simple example. So let's say x of t is 1 plus 1/2 cosine 2 pi t plus sine 4 pi t plus 2/3, I don't know where these numbers came from, but cosine 6 pi t. It's made up. Okay? So what is the, is this periodic? What is the fundamental period? So the period for that is 1, for this is 1/2, for this is 1/3. So they meet at 1. Alright? So t is equal to 1. That means our fundamental frequency is 2 pi. Alright? So the question is, can I write this as a weighted sum of terms that look like e to the j multiple k times 2 pi, right? So it's easy to do it in this case because cosine already can be split into a sum of e to the j 2 pi t plus 1/2 e to the negative j 2 pi t, right? Similarly, I can take sine and write it as 1/2j times e to the j 4 pi t negative 1/2j e to the negative j 4 pi t. And cosine again can be split as 1/2 e to the j 6 pi t plus 1/2 e to the negative j 6 pi t, right? So the terms that we see here, these two, so this one is stands for k equals, what is k? K1, right? Because it's just 2 pi t. K is equal to 1 here, right? For this guy, k is equal to -1, right? This means k equal to 2. This means k equal to -2. This means k is equal to 3. And this means k is equal to -3. So, with a very simple expansion of sine and cosine, this already split into a form that looks like the Fourier series form that we're after, right? So the coefficient of 1 is 1 itself, right? So then I can say A0, which is the DC component, or the coefficient of 1, is just 1. What is A1? The coefficient of e to the j2 pi. It's this times this, right? 1 over 4. What about a of -1? Same thing, right? 1/2 times 1/2. 1 over 4 again. What about the coefficient of e to the j4 pi? A2 is 1 over 2j. It's this, right? No coefficient in front of sine, so it's just 1 over 2j. A of -2 is this coefficient, -1 over 2j. And A3 is that times 2/3, which makes it 1 over 3. And A of -3 is again that times 2/3. It's also 1 over 3. All right? So there you go. We already have, without doing any real work, we already have the Fourier series coefficients, A sub k, for this periodic signal. I did not need to go beyond k equal to 3. Okay? Because it's just, nice and smooth function. It already comprises of sinusoidals, right? So I didn't really need very high frequency oscillations to recover the signal. Whereas in the square wave, I really needed to go really, really high. There was no limit to how large I should pick k. All right? So you're done. So for a simple example anyway, you found the Fourier series coefficients. Do you have any questions? So we only need 3 harmonics, second and third, and beyond that we don't need anything. So, well, let me ask you a question. Now, what do you observe about the coefficients AK and A negative K? A1 relative to A negative 1, A2 relative to A negative 2. Do you see a pattern again? They are again complex conjugates. For the same reason that we explained in the previous example, where we had only one frequency, right? For that to be real, the coefficients had to be balanced. One had to be the complex conjugate of the other. So that's a general property of Fourier series, actually. So if I look at this expression, let me write it. So this is called, it's an important property and it has a name. It's called the conjugate symmetry property. So when I write this property, I'm not going to assume x is a real valued signal at first, but there's a corollary to this property. We'll see what happens if x is a real value. Okay? So if x has Fourier series, Fs short for Fourier series, coefficients A sub k, then x star has Fourier series coefficients B sub k, which are related to A sub k by A negative k star. Okay? This is easy to prove. You just have to look at the expression for the Fourier series. X of t is the sum over k of ak e to the j k omega 0 t, right? If I take the star of x, I'm going to get everything inside the summation star, right? So I'll get AK star. And what happens when I start this? The power flips sign. So it becomes e to the negative j k omega 0 t. Okay? So let's define m to be negative k. So we're just changing the index. Changing how we count the index, how we count the terms in this summation. So this is equivalently then written as m going from negative infinity to infinity, a sub k star, but k is now negative m star. And then because negative k is m, we have in the power e to the j m omega 0 t, right? So, and you see this has already the form of a Fourier series, except that I'm using the dummy m instead of the dummy k, right, as an index. So that becomes, in this representation, the Fourier series coefficient Bm, right? And as you can see, Bm is equal to a negative m star, the complex conjugate of a negative m. M doesn't matter, it's just the way we call the index, so if you call it k, you recover this property. Okay? So this is true for any signal, even if it's not real valued, right? It's just a general property. But a corollary to that is if x is actually real, then x of t must be equal to x star of t for all t. And for that reason, the Fourier coefficients of the two things, ak and bk, which we know is a negative k star, must be the same. Okay? So this was bk, but I know that it's the same because the two signals match, right? So this is called basically the conjugate symmetry property and its implication for real valued signals. Okay? So that's why in our example we had this conjugate symmetry. So a negative 1 and a1 were closely related. Because it was real to begin with, its conjugate is itself. Okay? A2 is purely complex, so its conjugate is just negative of itself, and that's why exactly what you see here. And A3 is purely real, and its conjugate is therefore itself. Okay, so because x is real, we have this general property. Okay, so Fourier series. This is another indication that don't panic when you see these negative frequencies. Again, their role is to cancel things out and make them real. Right? So as you can see, the negative frequency components in the Fourier series expansion does not really contain any new information if you are dealing with real signals. They just, they just copy the coefficient of the positive frequency and take the conjugate so that they cancel out and give you a real term. All right, make sense? Do you have any questions? All right, so now we come to the main issue. So I'll go a little more and then we'll take a break. So if I, of course, give you a sum of sinusoidals, you can expand it in that form and you can say, hey, I have my Fourier series, right? But the real question is, what if I give you any periodic signal, perhaps something as as rough and edgy as this square wave, and how do I find the Fourier series coefficients of that? Okay, so that's the big question. Turns out it has an easy answer. Okay, so the question is, how do we find the coefficients? Finding Fs Fourier series coefficients, AK, in general, when things are not nice and sinusoidal to begin with. And the answer is very simple. We just need to go backwards. So the Fourier series expression is sum over all k, a sub k, e to the j, k, omega naught, t, right? All right? So what I'm going to do, now I'm believing this is true, I just want to get an expression for a sub k. All right? I want to solve for that coefficient, right? Here's the way to do this. You take this equation, multiply both sides with e to the negative j, some integer, pick your favorite, and let's call it omega 0 t, okay, times x of t equals sum. Now I have to multiply the right hand side with the same thing, right? But not much changes, so I can combine these two exponential terms. How do I write it as? I actually lost my color coordinate, lost its meaning. So let me, only because I started, and omega 0 t times k a k e to the j k omega 0 t. Okay, sorry for that. Now let's rewrite the right hand side. Sum over k, a sub k, e to the j, k minus n, omega 0 t. Do you believe me? Okay, and the left hand side is of course e to the negative j n, omega 0 t, x of t. All right. So just imagine k minus n, let's say, is equal to 1. Okay? How would I eliminate that term? How do I get to what operation would I need to do to this function so that, when I do that operation, I get 0? Take k minus n to be this 1. What do you need to do to a sinusoidal function? I asked it in a weird way, so I don't blame you for not giving me the answer I want. How about an integral? What's the integral of a sine over one period? 0, right? So I can take advantage of this property. So if I take the integral of both sides, say from 0 to t, right? Okay, then do that here too, 0 to t dt. So then what happens to this? Well, two things can happen depending on the value of k minus n, right? If k minus n is equal to 0, what happens? Then I'm integrating 1 over one period, so I get the period, t, right? If k minus n is equal to 0, right? If k minus n is any other integer, right? 1, 2, 3, whatever you want. Then what happens? It's now oscillating. It's really oscillating, it's not a constant. And then I'm averaging it over one full period or two full periods or three full periods, right? Depending on the value of k minus n. Therefore, I get 0. Okay? That's very convenient because that integration, as you can see, cleans up the right-hand side. You had all this ugly sum of over all k's. Now they're all dead. Only one remains. And that's k equals n, right? Everything else falls apart. Okay, so if k equals k minus n is different than 0. We're, of course, talking about integer k and integer n. All right, so therefore, the right-hand side, although it looks ugly, it's actually very simple. It's t times a sub n. All k's died, k equal to n survived. All right? So, well, then we're done. E to the negative j n omega 0 t x of t is equal to that. If I divide everything by the period, I have an expression for the Fourier coefficient a sub n. Okay? N had to be selected different than k here in this derivation, but I can just replace the index n with k. So I have the expression a sub k equals 1 over t, 0 to t, e to the negative jk omega 0 t x of t dt. There you go. That's how you find the Fourier series coefficients in general. You can apply this to any periodic signal you want. Yes? it is related to inner products. It is related to inner products. It is related to orthogonality. This basically comes from a space of functions which, when you restrict them to the period 0 to t, right, so they basically, I'm not sure if I should go into this, but the space of square integrable functions over 0 to t admit as a basis these basis functions, okay? If you want to look at it in that more abstract way, okay? And you can show that these guys are orthogonal to each other if for that space you define an inner product to mean u, v, being two signals, integral from 0 to t of u star t v of t dt. So essentially Fourier series amounts to switching the coordinates and using these basis functions and finding the coefficients. Okay? It's more elegant that way, but you do it more, down to earth way. Let's do it this way. I don't know what Fourier. I mean, the guy lived 200 years ago. I have no idea. I mean, if you look at his publications, probably you can get a sense. Well, I'm not going to do that. I don't have the time. I mean, it'd be interesting. I agree with you. It's interesting. Yes. Question? No? All right. Any other questions? Okay. So we're done. I mean, I could let you go for the rest of the week, but this is really how you find the Fourier series coefficients. Of course, we are not done. We are going to make a number of observations about this, but this is the essence. So one thing we should note, though, is A0. That's very special. The DC component. What is A0? When you put k equal to 0 in this integral, that exponential term just disappears. It becomes 1, right? So what do I get? 1 over t, 0 to t, x of t dt. So I'm averaging the signal over one period, and that's the DC component. If it's not 0, that's the bias term I have to add to my series. So that's very simple. And very often, the manipulations we have to do to find a sub k will differ, will not work for k equal to 0 because of some, you'll see some examples. And so first taking a look at A0 and just getting it out of the way is always good practice, because k is different than 0, will require more work. It's easy to see, so why not do it? The other thing I want to point out in this expression is, I just have to remember, so I said integrate from 0 to t, right? Why not from negative t over 2 to positive t over 2? You see, what I'm integrating inside is periodic with t, right? So what does it matter where I start integrating, as long as I integrate for an interval of length 2t, okay? I'm sorry, 1 capital T. So there's nothing special about 0 and t. Therefore, going forward, I'm going to use this bizarre notation. Instead of putting the lower end and the upper end, just put a sign next to it, meaning that this is periodic. Just integrate over an interval of capital T. Your problem where you start. Okay? 0 is, of course, a good candidate. All right, let's take a short break, 4 minutes. Start at 10 past. back, it seems. Oh, somebody's leaving. All right, let's continue. So let's look at examples. I don't really have much more in terms of theoretical development, so we'll look at examples and discuss them. So let's first talk about the square wave that I started out with. All right, so let's say the amplitude is 1, and and then it looks like something like this. So it continues periodically, right? Let's call the period t, and let's call the point where you jump from 1 to back to 0 t1. Okay, so this is a very general square wave. You can adjust the width, the duty ratio by adjusting the ratio of t1 to t. All right, so square wave. That's our first example. Okay, so how do I find the Fourier series coefficients? So the amplitude is 1. I told you A0 is the simplest thing. You should first always look at A0, feel good about yourself, see I know A0, I can do the rest type of thing. What is A0? It's the average over one period. Or why half? What period? So I told you need one period, doesn't matter where you start. But since we have a nice and symmetric function, instead of going from 0 to t, where you become 0 and then go back up to 1, that becomes a little messy, right? It's neater to start at negative t by 2 and go to t by 2. So I kind of prefer this interval. Okay, starting at negative t by 2 to t by 2. Okay, so that's the interval we're going to concentrate on. So if I average the value of the signal over that period, I take the integral over one period, that's the area of the square, which is what? What's the area? 2t1. And you divide that by capital T. Right. So that's your A0. All right, do you feel good already? Okay. So for k equal to 0, for k different than 0, we have to go back to that other expression. It has 1 over t in it. But it also has an integral of x times, in this case we're going to go from negative t by 2 to t by 2. We agreed on that because the signal is symmetric, so it's nicer that way. E to the negative j, k, omega naught. What is omega naught? Fundamental frequency, what is it? 2 pi by t times t dt, right? Well, fortunately, the square wave has a nice expression for x, right? It's either 1 or 0. It's 0 outside the interval negative t1 to t1. So all I have to do is to put 1 and replace t with t1. Agree? Because then it's 0, so it doesn't integrate to anything. Okay, so I have a nicer expression now. All I need is the integral of e to the negative jk 2 pi tt, right? So what is the integral of e to the j, I don't know, make a number, a times t? What is the indefinite integral? At. You need to put something so that when I take the derivative with respect to t, that something cancels. 1 over j alpha will do, because if I take the derivative of this, I'll get the coefficient j alpha, which will cancel with that, right? So that's what we are going to do. So basically this coefficient is all this k 2 pi by t business, right? So that is simply 1 over t. What did you just tell me? 1 over this guy, negative j k 2 pi by t of times k 2 pi over t t, right? And the limits of integration are t1 by 2 and negative t1 by 2. Not pi, it looks like pi. No. t1 by 2. Okay? Are we in agreement? So nicely the t is cancelled out. Okay? And what do I see here? I see e to the negative j k pi t1 by t, is that right? Plus e to the positive, and I substitute that in, j k pi t1 by t. Alright, are the signs wrong? Yes, as always. That should be a negative, right? No? No, they are both. What am I doing? Oh yeah, this one I'm subtracting, right? So that was negative, this is positive, right? Okay. Alright, so what does that look like to you? There's a minus sign. Sine, right? Sine, so 2j times sine, so this is equal to 2j sine of what? K pi t1 by t, right? But then because the signs are flipped, I'm going to get a negative sign. Does anybody have an objection to that? Do you agree? All right. So the good news is I already had some negative j and 2 hiding in the denominator, so they all nicely cancel out. Negative j's cancel out. 2's cancel out. So the remaining term is why did I cancel out this t? Was that intentional? Oh yeah, it cancelled with this. Yeah, okay. Alright, so bear with me. So k pi in the denominator, right? So is that true? Sine k pi t1 by t divided by k times pi. Is that correct? Agree? So there you go. This is our a sub k. But note that k equal to 0, this expression doesn't make sense. It's 0 by 0, right? So it's a good thing that we got this out of the way first. Why is there an implicit assumption in this derivation that k is different than 0? It came from, we assumed the integral as this form with this coefficient. That wouldn't have worked if it was just if k was equal to 0, right? So by the very derivation, we assume k equal to different than 0. So when combined, so this is for k different than 0, these two give us the Fourier series coefficients of a square wave. All right? It's good to look at a plot of these coefficients as a function of k. K is, of course, integer, right? So in the notes, you'll see such a thing. Yeah, what's happening? Yes, that's the Fourier. So, okay. So this is the derivation. Surprisingly, I did it right. So I took here t1 to be a quarter of t, right? So the duty cycle is like half because of the way we wrote it. So just imagine the period being 1 and t1 being 1/4, right? So then you have half of the time covered with 1s, the other half covered with 0s. So for that, you get t1 by t equal to 1/4. So this becomes sine pi k, right? So because of that, at every even number, you see, whenever k is a even number, like k2, k4, k6, I'm actually getting zeros, right? Alright, so a0 is the value we calculated before, and the odd valued a sub k's, odd value k gives us a k that looks like 1 over k pi times sine something, right? So those are the coefficients as k increases. And as you can see, they never disappear. No matter how large I go with k, I'm always going to have some little ak remaining there, right? That's because my task is very difficult, right? I'm trying to generate this guy by adding sinusoidals. I have to keep going to higher and higher and higher frequency sinusoidal components to be able to reproduce such a sharp turn here. Okay? Does that make sense? Okay, so in fact, if you look at, I'm just going to leap forward a little bit. So that's what it looks like. So if I add just the first three harmonics, okay, A0, A1, A2 is already 0, right? And A3, right? Just add up those components. You can only get this close, right? Because you're working with very slowly varying, sinusoidals. If I keep increasing K's, go all the way to the 7th harmonics, I'm going to get a little closer to the square wave. If I go to even higher harmonics, then I'll get closer and closer. Okay? In what sense do I get closer? We'll come to that shortly. But for now, that's enough for this example. Let's now talk about another example. Example 2. This is a triangle, periodic triangle wave. Alright, so this is a little harder to work with. Therefore, I'm not going to work with it all the way. I'll just show you how you would do it if you were patient. Not me, maybe you. So let's say the value is 0.5 at time equal to 0, and the period is 1. 0.5. Afterwards, it will keep repeating itself. That's what happens at 1. Okay? So because it's periodic, if I want to write an expression for x of t, it's enough to cover the function from negative 0.5 to positive 0.5. Again, we have an even symmetric function, so it's good to work with this interval that's balanced between the two sides, right? So how can I express x of t in that interval? It'd be messy to express it for all t, because you'll have all these going up and down, but within one interval it's easy, and now we know afterwards it just repeats itself. Would you buy it if I just gave you this expression? Stare at it for a second, and if you have an objection, raise it now. If not, you're good. You have an objection? No. So if t is 0.5 or negative 0.5, you get 0, as you should, right? If t is 0, you get 0.5. If t is negative, the negative absolute value term is actually positive, so it's increasing, right? Once t becomes positive, it's actually decreasing, so it brings you down to 0. Okay? Nobody's objecting to this, so we'll take this. So, what is A0? The DC. .25. All right. I guess that's the area of the triangle. No, we're talking about A0, right? Isn't this what you said?
Yeah.
So I'm just saying, isn't the area equal to 0.25? Yeah. Okay? When you scale it by capital T, which is 1, you get 0.25. A0 is easy. Now, AK is less easy. So we're going to have to do an integral of first 0.5, right? 0.5 e to the negative j k 2 pi by t, but t is 1, right? t dt. That goes from negative 0.5 to 0.5 dt. So I only took into account this part, right? That's the first term that we have to integrate to find ak. For the second term, we have to analyze two subintervals because they have different expressions. From negative 0.5 to 0, that looks like positive t, right? This is equal to positive t when t is negative, right? So that is t times e to the negative j k 2 pi t dt, right? And then I go from 0 to 0.5. Now I'm going to look at the positive part of this, which is negative t, right? So therefore, this will have a negative sign, t e to the negative j k 2 pi t dt. So to find ak, you really have to endure these three integrations. The good news is the first integration is easy. You don't even have to integrate. Just stare at it for a second and you should scream and answer. Remember, k0 we took care of. And so we're dealing with k's different than 0. So k0 would have made this term constant, right? But that's out of the question now. So we have k1 or 2 or something like that where this is oscillating. And therefore it's completing one full cycle over the integration period. So it will integrate to the best possible scenario, nothing, right? 0. Okay? If you don't see this, you can just go through the things like this and you'll get a sine, something like sine k 2 pi t, and no matter what integer k I plug in, I'll get 0. Okay? Make sense? Alright? So this one, there is no short answer to that. Okay? It would need a young mind like yours to go back to the calculus books, remember how to do integrals of this form. So what comes to mind? What kind of term names for integration by part? I never like that stuff, so I'm not going to do it, okay? But somebody at some point has done it. Every book has this example, okay? So there's an answer to this, which I'm not going to write, okay? I'm just going to call it, the answer is going to depend on k, because we're integrating over t, so t disappears, right? K remains. So I'm just going to call it alpha of k, whatever that is, all right? Now I have one more term to deal with that looks as bad, right? But the good news is the two terms kind of look similar. In fact, with the change of coordinates, if I define s to be negative t, this whole term looks like 0 to 0 to point. No, actually this becomes negative now because I'm changing s to negative t. S e to the j k 2 pi s ds. Probably I'm messing up the sign somewhere. I think it's good. Yeah, now you change the... Anyway, so something like this. Minus, I'm not sure. You can check this. But the good news is, after you look at it carefully, this comes out to be alpha of negative k, right? It has almost the same expression with t playing the role of s, right? They both have positive no, wait. Because, when they are both negative. What is happening there? Because one side I'm doing the integration. Yeah, this would be positive 0.5. Sorry. Okay. So anyway, with this change of variables, you make them look very similar, except that the k has a different sign. Okay. So then, if you have the patience to do one of these integrals, you know the answer to the Fourier series coefficients. It's going to be alpha of k plus alpha of negative k. Alright? So that expression for alpha of k exists somewhere. And I'm not going to even write that, but it looks prettier when you add to alpha of k, because alpha of k has some complex things in it. When you add to it alpha of negative k, those complex things clear out, and you get a nicer expression that is pi squared k squared, 1 minus cosine pi k. Okay? So once again, just like in the square wave example, when k is even, what happens when k is when k is odd? What happens when k is even? When k is even, like 2, you get 0, right? So 0 when k is even. And when k is odd, this number is really 2, right? Because you're looking at negative 1. 1 minus negative 1 is 2. And that 2 cancels with the 2 in the denominator, so you get 1 over pi squared k squared when k is odd. Okay? So the summary is a sub k, there are 3 distinct cases, 0.25 when k is equal to 0, 0 when k even, except when k is different than 0, except when k is equal to 0, and then 1 over pi squared k squared when k is odd. Okay? And there you go. You have the Fourier series coefficients. So now I'm going to show you what those coefficients look like as a function of k. Where am I? Here. That's what they look like. Alright, so you can see for even k's, k equal to 2, 4, 6, etc. is 0. Now let's compare this because both plots are given only from negative 20 to 20 in that range of k. So the first plot here was for the square wave, right? And this one is for the triangular wave. Do you see, unfortunately I don't have them side by side, so I'll keep flipping back and forth until somebody volunteers to make an observation about, just qualitatively, what is roughly different. I mean, there are many differences, of course, but, if you don't give me the answer I want, I'll just give you more hints about what I want to hear. Okay. So for the triangle, these higher harmonics, so this is the square, right? So this has a heavy tail, sort of, right? I mean, these AKs take a long time to die out, right? These terms. That area is pretty chubby, right? I mean, it still has a lot of value under these AKs, even when K gets very large. Whereas if I look at the triangular wave, those come very close to 0 really quickly. So why do you think the difference is? Why do you think the square wave needs, larger values hidden in these AKs when K is getting really big relative to the triangle? Square wave is an abrupt thing, right? So the triangle is relatively smooth. You just go up, go down. It's not such a big deal. But the square has jumps. It has a discontinuity. So recovering that sharp change requires really strong high-frequency term to produce that sharp transition, right? Whereas the transition in the triangle is smoother. So it doesn't take that, you still need to fully reproduce the triangular wave. You still need a k is k going to infinity, as you can see from our expression here. But the coefficients are dying down quickly. You see, you have 1 over k squared in the denominator. That means that goes down to 0 fairly quickly with k. Whereas in the other expression for square wave, we had a k in the denominator. That takes longer that gives you a heavier tail, right? So that's because of the shape of the signals. One signal is very abrupt, and it needs high frequency oscillations to be able to reproduce fully. The other is smoother and it's more chill, and doesn't need very strong high frequency components to reproduce. Does that sort of make sense? If it doesn't now, by the end of like 2-3 more weeks, you'll all think about frequencies and nothing else, and you'll be happy to be introduced to Monsieur Fourier, who gave us a different way of looking at signals. All right. So, any questions? Yes. I don't think so. There may be, I don't know. I can't say off the top of my head. Yeah, I mean, square wave requires some negatives. I don't have a good answer, to be honest with you. Okay. So, all right, let me go back to what I was writing. So let's go back to this Fourier coefficient business, this Fourier series business. So where did we do this? Here. So this is the expression for Fourier series, right? So I've been a little too liberal in writing this, right? What does this even mean? X of t is equal to this infinite sum. That sort of assumes that whatever I see in the sum will converge to a nice number, and that will reproduce the original signal, right? So that was sort of a imagination, or it was what we wanted to have, and we started out with this and decided how we should select the coefficient so we can recover the signal. But the question is, does the sum that I see on the right hand side, does that even converge? Does it converge in the first place? Or if it does converge, does it converge to x of t? Right? So those are valid questions that must be answered to make sense of these Fourier series representations. So fortunately, not Monsieur Fourier, but the German mathematician Dirichlet, gave an answer to this question. A very nice convergence result. So the question is this. Before his answer, the convergence question is the following. We'll postpone that for a while. Ask the question first. Does sum over k, a k e to the j k omega 0 t, which is our Fourier series, converge? Right? How do we know if it converges? To ask this question a little more precisely, here we set k from negative infinity to infinity, right? So let's make this a limit of something. So let's define a signal x sub m of t. So more precisely, I'll ask the same question a little more precisely. If I define this sum k negative m to m. Now it's a partial sum, but it's a finite sum. I'm only adding terms from k equal to negative m. M is a given integer, right? To positive m. A k e to the j k omega 0 t. The question is, if I take this partial sum, and if I fix a point in time, so more precisely, if we define xm and choose a point in time, point t equals tau in time, can I claim that at that point, this function xm of tau, this partial sum, as I increase the sum, as I take, m bigger and bigger, does that, as a limit of m going to infinity, does that really give me x of t? Okay, so that is the convergence question. So does that make sense? Because when I write k going from negative infinity to infinity, really I mean I'm dealing with a signal of this form, and I'm taking m to infinity, right? So the question is, as I take m to infinity, should I expect that this limit will exist in the first place? And if it does, will it converge to the value of the signal at that point in time? Tau, right? Not t, tau. We fixed the time, right? So in that sense, I fixed tau. So I'm only looking at one point in time. So really think of it as a sequence in M, right? I'm looking at one point in time, and I want to see what happens to that as I keep increasing M. Does that value, xm of tau, converge to the actual value of our signal, periodic signal, at tau? Okay, that's our convergence question. Do you agree that's a meaningful question to ask and a meaningful thing to expect if we are to use Fourier series? All right, so that's the question that Dirichlet answered. His answer was, I didn't even tell you what the answer is. Yeah, I pick any particular point in time tau. Every single point. Choose any point tau, and I claim that. Okay? And Dirichlet said yes under some appropriate continuity conditions. Let me just tell you what he said. Probably he answered your question better than I can answer your question now. His answer is conditional yes. He assumes a certain type of continuity. Okay? He assumes x is piecewise continuous, meaning that it's continuous everywhere except at a few points here and there, at a finite number of points. Okay? Piecewise continuous, and its derivative is also piecewise continuous. So that's all he's asking from the signal to give this type of convergence result. The piecewise continuous derivative. Then there are two cases. Once I pick any tau, if I happen to pick the time tau where that signal was continuous. So by piecewise continuous, we allowed ourselves to have discontinuities like this, right? But let's first say, so this is our tau, right? Let's first say we pick tau, t equals tau, at a continuous point, right? Then the answer is simple. The two cases, A, if x is continuous at that point tau, then I can indeed say the limit as m goes to infinity of x sub m tau is x of tau, right? That's the kind of result we want to see, right? But what if I choose, that's case B, if x has a jump at tau. So what if I pick my tau to be here? Exactly where the jump occurs. Okay? So in that case, if you have limits from the left and right, so I'm going to call this limit x of tau minus, that's the left limit. Okay, that's where I converge to as I'm approaching it from the left. And as I approach it from the right, let's call it x of tau plus. Okay, because I'm coming from the positive side, right? Then the limit as m goes to infinity of xm of tau depends on these two limits. Guess what it is going to be? Take a wild guess. It's the average of the two. I mean, of course, it's a guess. You don't have the proof or anything, but it kind of makes sense. Tau minus plus x tau plus. Right? So that's all that he said, and that's rather satisfying. So his main assumption is piecewise continuity, which we have for both the square wave example and the triangular wave example, right? They are both piecewise continuous. The square wave is actually discontinuous, but it's piecewise continuous, right? And the triangular wave is fully continuous. Its derivative is a discontinuity, though. But that's allowed under these conditions. Okay, so what would you then expect for the square wave? Let's start with the simple case. Triangular wave is continuous, so this is true. Okay, fix any point tau, see what happens as m goes to infinity. You should be converging to the true value of the signal. In other words, your series will converge, so the Fourier series makes full sense. Okay, and here we go. This is showing the partial sum. When I look at the sum from k equals -3 to 3, I only, of course, included 3 harmonics, right? I can only get so close to a triangle, but it's still not bad, right? Already with m equal to 3. If I increase m to 7, it looks more like a real triangle. M21 is getting pretty close. It's missing the top corner a little bit. M51 is even closer. You can keep going and you'll get closer and closer to an exact triangle. Alright? So this is really part A of the convergence theorem we discussed. Fix any point in time. Okay, see what's happening to x at that, to x sub m at that time, and you'll get closer and closer to the actual value of the triangular wave. Clear? Any questions? No. Now, if I look at the square wave, I expect to see convergence to 1 or 0, right? Depending on where I am, where I pick my time point in time. What if I pick the point to be exactly the jump point, where I jump from 0 to 1 or from 1 to 0? I should be converging to 0.5, and that's exactly what you see. So this is a similar plot for the square wave. So I'm reconstructing a square wave from those sinusoidal terms, but truncating at m. And this is showing you different values of m, right? M equal to 3 is questionable, 7 is not bad, 21 is okay, 51 is it's closer to a square wave. But you can see at the discontinuity, there is no convergence to 0 or 1. You're just converging to the half point. You're at the half point, right? You see that, right? So that really is an illustration of part B in the convergence theorem. At the discontinuity, you will converge to the midpoint. All right? All clear? Okay. So when you look at this picture, does something bother you? Didn't I just tell you that this? Didn't Parrot briefly tell us that the Fourier series will converge to the original signal? It has these little ripples in the corners, right? When people first observed them, they thought it was some mechanical, jitteriness or some mechanical failure of some sort. But then somebody came along. That one is actually American, Gibbs. Okay? So we had the French, we had the German, we had the American. He explained that this actually is real. It's not because you have some numerical error in your computation. It is to be expected from the Fourier series expansion. Okay, so for that reason, it's called the Gibbs phenomenon. Let's be more accurate about what Gibbs phenomenon is. You have these ripples near the discontinuities, and they don't go away. You might hope that as you increase m, they will disappear, but they are there. The only change when m is becoming really large is that those ripples are getting compressed and being concentrated near the discontinuity, right? But they don't go away. They are still there. Okay? In fact, you can show, or somebody, probably Gibbs himself, showed that you have something like 18% overshoot in xm of t, right? So at its highest point here, or here, or here, it goes to something like 1.18 or something close to it, right? And that peak value never goes away. Well, the only thing that changes as I increase m is when the peak happens. It happens closer to the discontinuity. Okay? But it's always there. Right? So that's called Gibbs phenomenon. I hope you have the question that I have. That's the question I want to address. Thank you for asking. It's almost like a planted question, yes. Well, you answer. Somebody should be able to give an answer to this question. So is this really at odds? Is Gibbs phenomenon at odds with Dirichlet's convergence result? No, Dirichlet was a reasonable man, and he also framed his theorem carefully, right? He didn't say, he claimed point-wise convergence. If I fix a point in time and see what its experience as m is increasing, it will converge to the real value, right? He did not say, if I look at the graph of xm of t, which you're looking at here, that graph will converge to the graph of x uniformly. He didn't say that. He just said, if I fix a point on the graph, let's fix this point on the graph. Okay, so let's fix this tau, right? I fixed that tau, so I'm looking at xm of tau, which is 1.18, right? Not good. I'm at m equal to 7, right? I stay here and see what happens as m is increased. Well, guess what? Once m increases, because the ripples are being concentrated closer to the discontinuity, to the jump, they are going to leave me alone, right? They'll go away. So when m is equal to 21, my tau is somewhere here. I'm in this area, right? And 51, I'm even closer to 1. Okay? So the convergence claim we have is point-wise. That does not contradict the Gibbs phenomenon. Does that answer the question? Well, so these are different notions of convergence, right? So what ideally you'd like to, when you look at a picture like this, what you want to see is those peaks also diminishing, right? That would be more like what's called uniform convergence. Whereas we're only claiming point-wise convergence. They are different things. There are, famous examples of this, simpler than that, right? Let me just give you an example. So take a function like this. Family of functions, right? So let's say a triangle with value 1 that comes back to 0 at time 1 over m. Okay? Call this function fm of t as a function of t, right? Does this function converge to 0? Well, if I increase m, it gets sharper, gets sharper, gets sharper. Graphically speaking, it does not, right? There's always like a peak there. Some needle is always there, right? So it is not uniform convergence in this sense. But it is point-wise convergence, because if I fix any point tau, let's say pick this point tau, for some m I may have hit the peak, but then as this guy gets compressed, I'm safe. I'm staying to the right of that, right? So this is an example of point-wise convergence to 0, a function that's uniformly 0 function, not uniform. So when I say uniform, for the purposes of this course, it's enough to imagine the graphs converging to each other. So this is a simplified version, essentially, of the type of convergence we are seeing in the Gibbs phenomenon. We are seeing point-wise convergence, but not uniform convergence. So Fourier series gives us point-wise convergence, which for all intents and purposes are enough in this course. In the remaining 5 minutes, do you have any questions, first of all? Yes. All right, you just have to be a little patient. So we'll have. So these are for. So far, we're only dealing with periodic signals, and then we'll extend this to signals that are not periodic, and then we'll expand it to signals that are finite duration. And so the answer to your question will gradually come. And Alex, who is looking very enthusiastic, is actually going to give you a demo at some point where you'll hear sounds and see frequencies on the scope and things like that. So that question will be answered in great detail. All right? Good enough for now? Okay. So let's finish with a couple of properties of Fourier transform. So we already saw one property, which is the conjugate symmetry property, which implied that if we have real valued signals, the positive and negative Fourier series coefficients will match. They will be complex conjugates, right? So that was one key property. There are many others. One really vanilla, simple property is the following. If I take a signal x, I'm going to start introducing weird notations now, but you'll know what I mean. What do I mean by that? Take a guess. X is a signal, it has the Fourier series coefficients a sub k, okay? Y is another signal, and it has Fourier series coefficients b sub k, right? So linearity property of Fourier series says that if I compose a new function, and of course, x, y have same period, okay? Because now we're going to add them up. Same period. So if I take take x multiplied with an amplitude a and multiply b with y, guess what Fourier series coefficients this sum would possess? That sum is again periodic because they have the same periods, right? So what coefficient would you expect? Big A AK plus big B BK. Very simple result that immediately follows from the formula we have for calculating the Fourier series coefficient, right? Because it's simply an integral, expand out the integral and you'll get this. Okay, I won't even bother with that. That's one. Two is time shift. If x has Fourier series coefficients AK, and if I define a new signal by x of t minus t0, so I shifted the original signal, I dragged it, right? So it turns out x hat, of course it's going to be periodic again, and its Fourier series coefficients will be AK multiplied by k 2 pi by t t0 times AK. And obviously if t0 is 0, that contributes nothing, so you recover AK. This is also very simple to see. Again, plug into the expression for a sub k, the integral expression. X of t minus t0, define t minus t0 as a dummy time. And the exponent, the t in the exponent will then have to be the dummy plus the t0 term. And out of that you can extract this term. That's all there is to it. Okay, very simple. The third one, and I'm really going to leave it at that. That's an important one though. It's the time reversal property. Again, I'm not going to prove it because it's simple to prove. You should all do it by yourself. If I define x hat of t to be a time reversed version, so I flip x and I call it x hat. Turns out x hat has Fourier series coefficients b sub k that obviously must be related to a sub k in some way, and the relation is a of negative k. That's very nice, easy to remember. You flip time, you flip the Fourier series coefficients in k. All right? As simple as that. And the nice corollary to that is the following. If x is even symmetric, that means x hat and x are the same things, right? So bk should be the same as ak, therefore ak must be equal to a of minus k. So I must have symmetry between the coefficients, right? Does that make sense? And if x is odd, symmetric, then x hat is negative x of t, that means ak will be negative k of negative k. Right? So if you combine this even symmetry property, take this even symmetry property and combine it with the real property. When they are real, when x is real, I know the complex conjugate property, right? AK and a negative k are complex conjugates. I also know if x is even symmetric in addition, that the two must be equal. Therefore, when is a number equal to its complex conjugate? If it is real, right? So the conclusion is, if I have a real and even symmetric signal, its Fourier series coefficients are real. That's exactly what we saw when we looked at the Fourier series coefficients of the triangle wave. Nothing imaginary here, right? Same thing with the square wave. Where is my square wave? Here. AK, the expression for AK is purely real. That was not a coincidence. It was because x was real valued and even symmetric. All right, I'll stop here.